Hi, welcome back guys, and hello to any new subscribers, hello to all my Year 10s and Year 9s if you're watching this as well. We're looking today at equilibrium again and how it's affected, how the position of an equilibrium is affected by changes in pressure or concentration. And in particular we're going to look at how they can be used to manipulate a reaction. So you should remember from last lesson that Le Chatelier's principle said that when a reaction is at equilibrium, the system will try and oppose any changes that you make to it. And we looked particularly at temperature. We decided that in any chemical reaction, reversible reaction, if the forward reaction is exothermic, then the reverse reaction will be endothermic, and for the same energy levels. So this leads to the situation where if the forward reaction is exothermic, releases heat, and we start to heat up that reaction, the reverse reaction will actually will start to happen more. That will be the favoured reaction, as the reaction tries to balance out the changes that we're making, tries to cancel those out, moves in the endothermic reaction, so starts absorbing the heat that we're putting into it. But today we're going to focus on how pressure in gases and concentration in reactions involving liquid reactions or solutions, how they affect the position of equilibrium. And this is higher tier. So starting off with pressure. If we have a reaction involving gases and it's at equilibrium, if we change the pressure, we change the position of the equilibrium. So we change how much product is made, and this is useful for adjusting how much product you make, your yield of product. If we increase the pressure, it makes the equilibrium move and shift towards the side that's got the fewest molecules of gas on. Decreasing the pressure, if we decrease the pressure when it's reached equilibrium, then what happens is the equilibrium shifts towards the side with most molecules of gas. Now, to increase pressure, we could do this by adding more gases into the reaction mixture. Even ones that don't react, we could do it by making the reaction vessel smaller, by compressing it with a piston, for example, or we could make the reaction vessel bigger for decreasing the pressure. Now let's have a look at what this means for a reaction. And our first reaction is here. We've got sulfur dioxide, a gas, plus oxygen, gas, makes sulfur trioxide. Now you can see very quickly that this reaction isn't balanced. We've got one sulfur on this side, one sulfur on this side, but we've got 2 plus 2, 4 oxygens here and only 3 here. So the first step is to balance this equation. So give it a go, see if you can do it. And put it on pause if you've not done so already, and we'll have a look at the answer now. The answer is 2 sulfur dioxides plus 1 oxygen makes 2 sulfur trioxides. So this is our balanced equation. Now we can see now how many moles of gas we've got on each side, or molecules on each side. The reactant side, the side in red, we've got 2 molecules of sulfur dioxide, 1 molecule of oxygen, so 2 plus 1 is 3 molecules of gas in total on the left hand side, on the reactant side. On the product side, we've got 2 molecules of sulfur trioxide. That's the only thing. So we've got 3 molecules on the left, 2 molecules on the right. Therefore, the product side here, we've got fewer molecules of gas, and if we go back to what we just looked at, if we increase the pressure, we're going to make more of the side with the fewest molecules. This is the side with the fewest molecules, the sulfur trioxide side, so we'll end up making more sulfur trioxide. If we do the opposite and we decrease the pressure, we'll end up making more of the products, more of the sulfur dioxide and the oxygen. Okay, so to explain this again, we increase the pressure at equilibrium, the equilibrium will move and will produce more of the side with the fewest molecules of gas, and in this case it will make more of the sulfur trioxide, more of the product. The equilibrium will move to the right. If we decrease the pressure, the equilibrium will move to the side with most gas molecules. So in this case it will move to the left and will make more oxygen and sulfur dioxide to balance out, to cancel out what we have done to the equilibrium position, okay, by our change to the reaction. Quite simple. Another example, if we take methane and react it with water, we can make carbon dioxide and we can make hydrogen gas, and this reaction is reversible. So, if we increase the pressure again, we will move the product, move to produce more of the side with the most molecules of gas. So we need to work out which side has got the most molecules of gas. And if we have a look, CH4, 1 molecule of gas, H2O, 1 molecule of gas, and on the other side we've got 1 molecule of CO, carbon monoxide, and 3 molecules of hydrogen. So we've got 4 molecules on the right, 2 molecules on the left. So the right hand side, the product side, has got more molecules of gas. And a little point to make very, very clear here is that every gas, every molecule of gas gives the same pressure. When it comes to making gas pressure, it gives the same pressure as any other molecule of gas. So a molecule of methane would give you the same amount of pressure as a molecule of water vapor. It's the same amount of pressure as a molecule of carbon monoxide, providing the temperature is the same. So in this reaction, if we increase the pressure, we're going to make more reactants because there are fewer molecules on this side. If we decrease the pressure, we're going to make the side that's got the most molecules of gas, which is the right hand side, the carbon monoxide and the hydrogen. Now, how concentration affects equilibrium. How the concentration affects it is slightly more complicated in a certain way. It might take a little bit of thinking about, but it's still not. Once you figure it out, once you get your head around it, it's quite easy. So, if we change the concentration of a reactant or a product when a system has reached equilibrium, the equilibrium is going to change to oppose that change. So if we increase the concentration of a reactant, so if we add more reactant in, for example, it will use more of it and we'll make more product and bring itself back towards a balance, although the concentrations won't stay the same. If we decrease the concentration of the product, so if we take some of the product away, again the equilibrium will shift and we'll end up making more product. And we've got some examples to show that. So, sulfur dioxide and oxygen again to make sulfur trioxide. If we add more sulfur dioxide, more of the SO2, if we increase the concentration of it, then the equilibrium position alters itself, makes more sulfur trioxide to reduce the amount of the sulfur dioxide we've added in. As I said, you can think of these reactions a bit like something that's really, really stubborn or obstinate, and it's going to try and oppose everything you make it do. So if you increase the concentration of sulfur dioxide, the reaction is going to be stubborn and make some more sulfur trioxide by getting rid of the sulfur dioxide. If we remove the sulfur trioxide, the other thing we can do, we remove it, we somehow tap it off, then again the equilibrium position gets upset, and because there's not a lot of this left, more of the reactants break down to make the sulfur trioxide. And again, you can think of it this way, is you've constantly got a back and forth reaction here. When the sulfur trioxide breaks down spontaneously, it makes these two things. If there's not so much sulfur trioxide, then there's not so much of it to break down to make the oxygen and the sulfur dioxide. Therefore, these concentrations will fall and the concentration of sulfur trioxide will go back up. It's fairly obvious, I hope, that adding more of a reactant to a reaction will make more of the product. That should be fairly obvious because we've added more of the thing that's reacting to make the product. Now, on the removing of the product, you can think of it a bit like a factory line. You can think if there's too much product in your factory at the end of the production line, at the end of the conveyor belt, then there's no space to make any more. The conveyor belt's full, you can't make any more product because there's nowhere to store it. You need to get some of that product out of the factory before you can start making more. So that's one way of thinking about it. So a little summary then. When we change pressure at equilibrium, the reaction will move to oppose the pressure change. So it'll move to the side with more or less gas molecules depending on what we've done. If we increase the pressure, we end up making more of the side that has the fewest molecules. If we decrease the pressure in a equilibrium reaction, then we make more of the side with the most molecules. If we increase the concentration of our reactants, we make more products when we're looking at concentrations. And if we remove our products, lower the concentration, in other words, we make more of the product. The reaction makes more of the product. More of the reactants react together to make more product. And so this can be all used in a chemical reaction. Now in our next lesson, we're going to look at a specific example of a chemical reaction, reversible reaction, called the Haber process, and how that can be manipulated to give us the best yield and the best rate. So bringing in those two things. Anyway, this is higher tier, and I know it's quite complicated at times to get your head around, so if you've got any questions, please ask them. Don't hesitate. My classes, if you can ask them in Teams, anyone else who's watching, you can ask them in the comments here. Anyway, thank you very much, guys. Please click the subscribe button if you've not already done so, and remember to like and to share. And thank you very much. See you soon. Bye bye.